This chart highlights two very different technological trajectories between 1970 and 2010. While the cost of computing power plummeted and its capabilities increased thousands of times over, the cost to launch a kilogram of payload into space stayed absolutely flat. The reason for that stagnation comes down to a fatal design flaw in the business model. For 40 years, the standard practice was to build highly sophisticated, multi-million-dollar rockets, fly them once, and crash them into the ocean after a single use. Russian space pioneer Konstantin Tsiolkovsky famously noted that Earth is the cradle of mankind, but you cannot live in a cradle forever. The problem was that the sheer expense of throwing away hardware every time we left the atmosphere made leaving that cradle economically impossible. That economic barrier finally broke when engineers figured out how to recover and land the first stage of a rocket. By flying vessels multiple times, companies like SpaceX with their heavy lift vehicles, and European developers like PLD Space using parachute recovery for their Miura 5 rockets, slashed the cost of space launch by a factor of 5, dropping it from $10,000 a kilogram down to $2,000. Removing the high cost of single-use rockets unlocked a multi-billion-dollar off-Earth industrial sector. The immediate result of cheaper launches is the rapid commercialization of low Earth orbit. This zone, extending roughly 2,000 kilometers above the surface, is the first active tier of the new space economy. Lower payload costs allowed for extreme miniaturization. Where standard satellites used to be the size of a school bus, aerospace engineers can now pack navigation and communication hardware into a CubeSat, a standardized 10 by 10 centimeter box weighing only about 1 kilogram. Companies like Allen Space are deploying these small devices for highly specific practical applications. Their LUM-1 CubeSat orbits the Earth to actively track and monitor global wildfires, relaying early detection data directly to emergency services on the ground. The reduced barrier to entry has also opened the door to civilian passengers. Private aerospace companies are routinely flying non-professional astronauts to the edge of space to experience microgravity. While initial commercial flights focus heavily on tourism, the underlying technology paves the way for suborbital point-to-point travel. By flying up through the atmosphere into the near vacuum of space, where aerodynamic drag drops almost to zero, transit times between distant cities collapse. This animation illustrates how a suborbital flight path arcs out of the atmosphere. Instead of spending 18 hours on a traditional commercial jet, a passenger could travel from Los Angeles to Sydney in less than an hour. Beyond transport and observation, the physical environment of low Earth orbit offers entirely unique conditions for manufacturing. The absence of gravity and atmospheric pressure allows materials like liquids and gels to mix and form without settling or collapsing. The company Foam Zinc proved this by manufacturing specialty optical fibers aboard an orbital platform. They discovered that drawing fluoride glass in microgravity prevents crystallization, resulting in a cable capable of transmitting data far more efficiently than anything produced under Earth's gravity. Low Earth orbit has shifted from an exclusive government research lab into a profitable industrial park. It proves that certain products and services are simply better when they are built off Earth. To push further out into the solar system, we have to stop packing everything we need from Earth. Expanding past orbit requires breaking our reliance on terrestrial supply chains and extracting resources directly from places like the Moon. Commercial prospectors are already mapping those resources. Lunar Outpost has developed a fleet of compact rovers, known as MAP, designed to scour the lunar surface for usable materials like water ice. Because much of this ice is hidden inside permanently shadowed craters where traditional cameras are useless, these rovers use LiDAR, a laser ranging and detection system, to navigate autonomously and map mineral deposits in total darkness. Before we can actually mine those deposits, scientists need to understand the physical properties of the soil. At the Colorado School of Mines, researchers run extensive tests on simulated lunar dirt, called regolith. To recreate the extreme environment of the Moon, the team uses liquid nitrogen to freeze the regolith down to -230 degrees. They then drive a steel probe into the frozen sample to precisely measure the mechanical forces required to drill into the surface. The ultimate goal of this research is habitat construction. By using concentrated sunlight to melt the native regolith, autonomous machines will be able to 3D print tools, radiation shields, and entire base camps without importing a single brick from Earth. The Moon has graduated from a site of exploration to an active proving ground for humanity's permanent off-world infrastructure. The commercialization of orbit and the industrialization of the Moon represent a transition. Space has evolved into an inhabitable industrial supply chain. This diagram illustrates the Kardashev scale, a framework for classifying technological evolution. Humanity is currently transitioning out of a Type 1 civilization, one that relies entirely on the resources of its home planet, and taking the first steps towards a Type 2 civilization, which harnesses the resources of its entire solar system. Leaving our home planet can feel unnatural, but from a strict biological standpoint, humans aren't truly native to the entire Earth. As a species, we are tropical animals, native specifically to the Kenyan Rift Valley. No human in their natural biological state could survive a winter night in northern Europe or Colorado. We only managed to spread across the globe by inventing life-sustaining technologies like clothing, controlled fire, and insulated shelters. The reusable rockets, CubeSats, and lunar habitats of the new space economy are the exact same survival tools, scaled up. We are using technology to adapt to a harsher environment, continuing an ancient instinct to leave the cradle and step into the solar system.